I'm Stephen Ware,
And I'm Rachel Farrell.
and we're coming to you today from the Narrative Intelligence Lab at the University of Kentucky. Our lab does a lot of research on algorithms for generating stories automatically, for things like video games and training simulations. We're specifically interested in algorithms that plan out a story in advance to ensure it contains all the necessary content. Narrative planning is a really interesting computational challenge. We call it the puppet master problem, because a single storyteller agent that's omniscient and omnipotent in its virtual world needs to search for a story that has all the necessary content, but where all the individual characters act realistically according to their intentions, wrong beliefs, and limited observability, and so on. The formal logical structure of plans has a lot of advantages in terms of what we can model, and one of the things we can model is salience.
When people experience a story, they segment it into events and store those events in short-term memory. Past events may be easier or harder to remember depending on what's currently happening in the story. Events that are easy to remember are more salient, and events that are hard to remember are less salient. There are at least 5 factors about the current event that can influence the salience of previous events. For example, if the current event involves King Arthur and is taking place in Camelot, then it's easier to remember past events that also involved King Arthur or took place in Camelot.
Modeling salience in a narrative plan makes our representation of the story richer. But it led us to wonder, can we use salience to help a narrative planner find solutions faster? In this short video, we define how we represent salience, do a quick salience analysis of solutions versus non-solutions to narrative planning problems, and finally test whether salience can speed up the search process.
Indexter originally mapped 5 salience indices onto narrative planning events so that the salience of past events could be measured based on their shared indices with the current event. Studies have also found other interesting applications for this model. One study measured choice meaningfulness and found that choices feel more meaningful to players when their options differ by at least one index. We also did a study that showed that we could predict people's choices for the ending of a story based on the indices that each ending shared with previous events that player had chosen, as long as those choices were meaningful in the sense that their options differed by at least one index.
Our goal is to translate this concept of salience into something we can use in a search algorithm. So we're intentionally using really simple definitions of each of these 5 indices. We say that 2 actions share the protagonist index if there's a character that's involved in both actions. They share time if they happen in the same discrete time frame, like the same day. They share space if they happen in the same location. They share causality if the earlier action has an effect which establishes a precondition of the later action. And for now, we don't implement the intentionality index. This is because our planner builds partial stories from start to finish, and you usually can't tell if 2 actions were taken for the same reason until you can look at the whole story. Finding some way to implement the intentionality index is one of the clear directions for future work. While a planning algorithm is building a story, it's generally trying to minimize the cost of a plan. Typically, this means minimizing the number of actions so as to find the shortest plan, or maybe minimizing fuel use or distance traveled or something like that. So to use salience to speed up story generation, we have to translate this idea of actions being salient with one another into a cost function for the planner to minimize. A narrative plan is a sequence of actions. We can define the salience cost of a plan as the sum of the salience distances between each pair of actions. So we'll add up the distance between the first and second action, the distance between the second and third action, and so on. We can define the distance between 2 actions based on the number of indices they have in common. Actions that involve the same characters, the same places, are closer together, and actions with different characters in different places are farther apart. We want this distance value to be between 0 and 1, but we never want the distance to go all the way to 0 for a reason we'll discuss later. To make sure distances never go to 0, we'll say that actions are always at least epsilon far apart. Epsilon is just a constant between 0 and 1 that represents the minimum possible distance between 2 actions. The rest of the distance, which is at most 1 minus epsilon, is determined by how many salience indices the 2 actions have in common. Distance is high when actions do not share indices, so we're actually counting how many indices they don't share. Or we can think of this as 1 minus the number of indices they do share. For now we've got 4 indices: protagonist, time, space, and causality. But to keep things general, we'll say that for however many indices we have, let each one of those indices be a function I, and we'll count 1 if the actions do share that index, and 0 if they don't. This 1 symbol here is called the indicator function. It returns 1 if this Boolean function is true, or 0 if it's false. This Boolean function I is the salience index. It's true when actions share the index. So when two actions involve the same character, the protagonist function returns true, and the indicator function returns 1. So now we've got a way to measure how close two actions are to one another. The notation is a little gnarly, but the concept is simple. Actions are closer together when they share more indices with each other, and the cost of a plan is the sum of the distances between its actions.
This is an example domain with 5 locations. One is a central crossroads that connects the other 4, and characters can only walk along those paths. The main character is Tom, who is trying to get a special potion and bring it back home. Other characters include a merchant who sells that special potion at the market during the day for 1 coin, and an armed bandit who lives at a nearby camp and wants to steal valuable things. Tom begins at home with 1 coin, and the story ends when he either succeeds in bringing home the potion or is killed by another character. So let's look at an example where Tom walks to the crossroads and then to the market and then buys the potion and then walks back to the crossroads and back home. The first pair of actions share all 4 indices. They both involve Tom, they both happen on day 1, they both involve the crossroads, and the first action has an effect that satisfies a precondition of the second action, since Tom needs to be at the crossroads in order to walk to the market. The salience distance between these 2 actions is the smallest that it can possibly be, which is epsilon. We found that an epsilon value of 0.4 works well in our domains. The second pair of actions, walking to the market and buying the potion, also has the lowest salience distance. They share a character, a time frame, and a place, and one enables the other, so they also have a salience distance of 0.4. Actions 3 and 4 have a slightly larger salience distance. They both involve Tom and day 1 and the market, but they have no causal connection. While buying the potion is necessary for the story, it doesn't enable action 4 to happen, so these 2 don't share causality, and their salience distance is 0.55. The last pair of actions again has the lowest possible salience distance, and we can add up all these 4 values to get the total salience cost of the plan. And if we divide that value by the number of actions, we can see that the average distance between actions is about 0.35. Here's another example. In this story, the bandit intercepts Tom at the crossroads and attacks him before he can get to the market. If you imagine filming these stories, the first story might be shot in one continuous take, but in this story there would probably be a cut between the first 2 actions. After Tom walks to the crossroads, it would cut to the camp to show the bandit walking to the crossroads. Both events need to happen before the attack, but they're otherwise independent threads, so it makes sense that the salience distance between them is a little higher. They both happen on day 1, and they both involve the crossroads, but they don't have a character in common, and one doesn't enable the other. The second pair of events do share all 4 indices, so they have the lowest possible salience distance. Again, add these values up to get the total salience cost of the story, and divide by the number of steps to get the average salience distance. So while the total salience cost of this plan is slightly lower than the first, we can see that the average salience distance between events is higher. Overall, the events in this story are less mutually salient with each other than in the first example.
Before doing a bunch of work to find out if our salience cost function could speed up a planner, we did a quick sanity check. We picked 3 storytelling domains from our previous work, one from an adventure game made in our Camelot story game engine, one that's a version of the plot from Indiana Jones and the Raiders of the Lost Ark, and one from a choice-based narrative that we used in a previous study on salience. We used basic breadth-first search to generate every possible sequence of actions up to a certain length in each of these domains. Then we looked at which sequences were solutions and which ones were not. A solution just means it's a sequence of actions that achieves the author's goal for the story and only uses actions that make sense for the characters. In all cases, the sequences that were solutions had a lower average salience cost than non-solutions. That's a good sign because it means that maybe if we prioritize searching for low salience cost plans, we might be able to find solutions faster. We're finally ready to find out if salience cost can speed up a planner. We're using our Sabre narrative planner, which is a forward-chaining state space search. That just means that it starts at the initial state and adds actions on to the end of a plan until it finds a solution. Search algorithms usually maintain a min priority queue that defines which partial plan it's going to add on to next. We can use salience cost for a few different kinds of search techniques, but we'll need to define a few terms first. Let's say that length is the number of actions in a plan, S cost is our salience cost, and H is a heuristic. In this context, a heuristic is just a function that tries to guess how many more actions we would need to add to the end of the plan before it will be a solution. The most basic kind of search that a narrative planner can do is breadth-first search, where it generates all plans of length 1, and then all plans of length 2, then all plans of length 3, and so on. There's also uniform cost search, where the planner always expands the lowest cost plan first. But in classical planning, cost and length are usually the same thing, so in that case there's no difference between breadth first and uniform cost search. And then of course we have everybody's favorite search algorithm A*, which minimizes both the cost already paid and the estimated cost remaining. We can use Salience to define variance on all three of these. Breadth first search runs into a lot of ties, so we can use Salience as a tiebreaker. Given two plans of the same length, Salience breadth first search will expand the one with the lowest distance between the last pair of actions. Since Salience cost is different from the length of the plan, we can also define Salience uniform cost search, which always expands the plan with the lowest Salience cost. And finally, we can define Salience A*, which always expands the plan with the lowest combined Salience cost and heuristic. Remember a few minutes ago when we talked about epsilon? That's the minimum distance between two actions. Epsilon needs to be greater than 0, so that every time you add an action to the plan, the cost of that plan goes up at least a little bit. Otherwise, some of these search algorithms wouldn't be complete. When we use a small value of epsilon, Salience influences the search a lot. And when we use a big value of epsilon, Salience barely influences the search at all. If we turn epsilon all the way up to 1, then we'd actually just be doing breadth first search again. The full results are in the paper, but the short version is that Salience can speed up a narrative planner in some domains if you choose a good value of epsilon. These graphs show different values for epsilon on the x-axis. The y-axis is how many partial stories the planner had to generate before it found one that was a solution to the storytelling problem. Salience, and therefore epsilon, isn't used at all in breadth first search and basic A*, and epsilon doesn't affect how we would break ties in Salience breadth first search, so these three lines are always straight. But epsilon does matter for Salience uniform cost search and Salience A*. Sometimes the Salience-based searches were always better for a problem, and for some problems you can find a value of epsilon that will do at least as well as the traditional searches. Usually performance improved as epsilon got larger, with one exception. On this problem, lower values of epsilon were better for uniform cost search. This means there's probably no single value of epsilon that will do well in all domains. So, in conclusion, the same model of salience we use to measure what people remember and expect from a story can also be used to speed up story generation. We can imagine at least a couple of reasons why this works. The first is Chekhov's gun. When a story starts with Tom walking to the crossroads, it's probably because Tom, the crossroads, or both are going to be important later. So when one action does a good job of building on and reusing stuff from past actions, it's more likely to lead to a story that works. The second possible explanation is that the authors of the story domains had certain solutions in mind when they created these domains, and perhaps they subconsciously designed the domains such that those solutions were easy to expect and thus had a lower salience cost.
Whatever the reason, we're excited about these preliminary results and the future work they point to. First, we'd like to see these results replicated in other domains that were written by authors other than ourselves. We intentionally used a really simple measure of salience distance that only considers neighboring pairs of actions, but by considering more indices or improving our indices to look at the plan as a whole, we might be able to get better results. Aside from being easier to find, we suspect that stories with a low salience cost might also be easier to read and understand, and we'd like to investigate that in future work. Finally, we have a forthcoming paper on using salience to measure story similarity, which is part of my dissertation work on clustering solution spaces.
Thanks for watching, and thank you to the U.S. National Science Foundation for funding this research, and to all our colleagues at the Narrative Intelligence Lab for their help and support.